Hello, everyone, and welcome to another wonderful day of PChem. So, we're going to continue our discussion of symmetry. So far, what we've mostly been talking about is how I can identify the symmetry of an entire molecule. But it turns out that we often care about things that are smaller than a molecule size. So we also care about how our symmetry elements or symmetry operations are going to apply to molecular orbitals. And unfortunately, while a lot of our molecular orbitals are going to have certain behaviors, a lot of these molecular orbitals we can assign to certain symmetry elements. So one of the major things we're going to need to do before we start applying our symmetry operations to our orbitals is actually we need to figure out how symmetry operations, or specifically their elements, go ahead and interact. And this is going to be a real foundational idea called group theory. So we're going to be trying to, over the next couple lectures, really analyze SO2. So sulfur dioxide has a nice C2V point group, same group as water because it's pretty much the same shape. And the C2V point group contains four major symmetry elements. So we have our classic element that's constantly ubiquitous, E. So this is our identity, which is essentially saying that if I don't do anything, I'll get the same image back. Gotta love that one. We also have one C2 axis, which we're going to define as running through the z-axis. So this C2 axis means that I've got a twofold rotation. So if I rotate the molecule 180 degrees, I'll get the same image back. And we also have two sigma v, or two vertical mirror planes, one in the plane of the molecule and one bisecting the two oxygens. Or we can think about this, one running in the zy axis, one running in the zx axis. And that's more or less the symmetry operations or elements that describe SO2. But it turns out when we have a group of operations like this, they actually obey an entire branch of mathematical descriptors called group theory. And group theory is a really powerful way to describe systems. It's a very concise way to take a big, massive data set and try and break it down to a little bit more concise rules of behavior. However, before I can use group theory, I have to make sure that my group, or that my set of operations, obey a set of rules. And so we've got four major rules we have to make sure our system obeys. First of which, one of our operations must be the identity. Must be this idea that nothing happens. Well, we know we have that because one of our four operations for C2V is the identity. And this is the reason why I said earlier that every single point group has to contain this identity operation. While it may seem fairly simple, it turns out to be mathematically one of the most important operations. The next major idea is that for every operation, which I'm going to call R here, there's a reverse operation of R minus 1. So let's go ahead and take our C2 rotation. So if I rotate my molecule 180 degrees, my reverse operation would be rotating it the other direction, 180 degrees. So if I have a clockwise rotation, my reverse operation would be the counterclockwise rotation. But it turns out with C2 rotations, I get very lucky because it turns out that the second 180 rotation also gets me back to where I started. So again, this will be my reverse operation. Another way to try and mathematically describe operations and their reverse ones is that if I follow my operation by the reverse operation, I should get back to the identity. I should get back to where I started. Now, one of the next important ideas is this, again, idea of how I can combine two operations together. So if I've got any two consecutive operations, so R and R prime, they're always going to be equivalent to some other operation. So if I do a uh, do a rotation followed by a mirror image, so rotation followed by a mirror image on the py orbital gets me back to, say, the identity. And this is an important idea, that if I start combining my various operations together, I'll always get another operation back out. No matter how I combine these two operations, it will always result in one of the operations of the set. So when I've got four operations, no matter how I combine them, I'll have one of those four operations as an output. And this is actually really big, because if I have a long string of operations, I can usually break them down one by one or set by set, two operations combined to make one. And then if I bring in a third operation, so I've got three operations consecutively, I can either say combine the last two or the first two, and it won't matter. And this is really huge because let's say I already know what r prime followed by r double prime is. This gets me a new operation, which I can then combine with r. And so this is a really important idea. And again, this result means that if I have a group, that I can essentially combine each set or pair of operations for each part of the symmetry group. Now, this, let's be honest, is a little bit of a mouthful and kind of abstract. So let's go ahead and apply this to our C2V point group. So we can see that all of these four operations from my C2V point group actually do form a mathematical group. So one of the things that we should note in this case is that C2 and our sigma V operations will always form their own inverse. So if I follow a C2 rotation with another C2 rotation, I'll get back to where I started. And the same thing also happens with the mirror planes. So if I take point A and I send it across the mirror plane to point B, and then apply that same mirror plane again, I get back to where I started. And so what we're going to do is essentially perform each set or possible pair of operations, r followed by r prime, and see what they give us back as a result. Now, this is going to give us 16 different combinations. So we're going to put this together in a table, but your book prefers to present this as a matrix. So it is worth noting that this table and matrix forms will be essentially identical. Now let's go ahead and start by walking through all of the possible combinations of symmetry operations. So first of all, E is our identity. This is the idea that I do nothing. So if I do nothing followed by doing nothing, the end result is I did nothing. Hopefully this makes sense. Or we also have this idea of I do nothing followed by a rotation gives me an end result of a rotation. Doing nothing followed by reflecting across the mirror plane gives me a reflection across the mirror plane. And doing nothing followed by a reflection across the other mirror plane gives me the reflection across the other mirror plane. Now it is worth noting, I forgot to address this, that we have our two different mirror planes. We're going to represent sigma V as the mirror plane in the XZ axis. So the XZ axis is going to be the one bisecting the two oxygen atoms. So the one splitting the molecule in two. And the YZ is going to represent cutting the molecule along the plane of the molecule. It won't matter quite so much in this case, but we'll hopefully illustrate as I apply these operations. But again, to where we're at, if I do nothing followed by an operation, it gives me the second operation. Conversely, if I perform an operation and I follow it with the identity, it gets me back whatever my original operation is. So if I do a rotation followed by doing nothing, it gets me back that rotation. So this is one of the reasons why we love the identity, because if I combine the identity with any other symmetry operation, it gives me that symmetry operation back. So these uh, these seven matrix elements are actually rather easy to figure out. So we love these guys. And you'll also notice that it doesn't matter the order in which I perform the operations. I'll have a symmetric matrix, which becomes which is also a huge advantage, as it doesn't matter which operation I perform first, I always end up in the same place. Now, let's go ahead and start playing around with these more complicated symmetry operations. So let's say I have a point, and then I do a 180-degree rotation. So a C2 rotation, I follow with another C2 rotation. Again, this gets me the identity. And this is, again, this idea that a C2 rotation and a sigma V mirror image are their own inverses. So if I combine them with themselves, I'm also going to end up as the identity, because performing the same operation twice is the same thing as doing nothing for both of these cases, which again is a wonderful result, and turns out to be true for almost all symmetry operations. Now, this gets me down to essentially just the combinations of C2 and sigma V's. So in this case, if I do a C2 rotation, so I rotate 180 degrees, and then I reflect across the sigma V axis, this is the same thing as having done a single mirror image across the sigma V prime axis. So these two symmetry elements, when combined, is the same thing as just taking a mirror image across the sigma V prime axis. And again, it doesn't matter in which order I perform these two operations. It will be equivalent. Now, let's go ahead and go a little bit more messy, and we can do a reflection across the across the sigma V prime axis, and then a reflection across the sigma V axis. And again, this gets me back to this C2 symmetry, or C2 operation. It's the same thing as doing a 180-degree rotation. And what you'll notice, if you try and apply any of these four operations to each other, you're always going to get one of these four operations back. And so this is actually rather wonderful, as plenty of chemical transformations and electron excitations are very similar to applying one of these symmetry operations. So if I do a series of manipulations of my system, I could essentially simplify it down to one of the end results. And this is also very important because it shows that while I may have a series of complex mathematical movements in my system, they all form a general group which will obey set rules. And we'll go ahead and explore more of the consequences of group theory next time, as we start more specifically looking at how symmetry operations affect all of our various p orbitals in sulfur dioxide. Till then, take care and stay healthy.